Hi friends, this is Rashekar, a GET faculty for electrical machines. Today in this video, we are going to discuss about open circuit test, simply called as OC test. Let's see this OC test. For example, I am taking a transformer here. I am taking a transformer. Let's see, this is my transformer. This is my transformer, and its secondary winding is open circuited. Its secondary winding is open circuited. When the secondary winding is open circuited, there is no current flowing in the winding. There is no current flowing in the winding because this is an open circuited winding. That's why no current flowing. And now this is my primary. Now this is my primary winding. In this primary winding, one ammeter is connected to know the current values, and one voltmeter is connected to know the voltage values, and one wattmeter also connected. Wattmeter also connected for power measurement. Wattmeter also connected, and here the supply voltage is connected. This is my circuitry. Here rated supply voltage, rated supply is given, rated supply, and this is our wattmeter. Because of no load, it is taken as W0, and here the current flowing in the winding is I0. This is the rated voltage V. So at this condition, flux produces, which is called no load flux, which is equals to phi naught. This is my transformer at no load, or simply open circuit condition. Now first of all, why we have to do this test? What are the aims of my test? What are the aims of my test? Why we are going to conduct this test on our transformer? First one, to find the no load losses. To find the no load losses of the transformer. This is very important. And next one, to find the no load parameters. To find the no load parameters of my transformer. No load parameters nothing but R0, X0, IW, I mu, and phi naught, etc. To find the no load losses, and next to find the no load parameters, and next to separate no load losses into hysteresis and eddy current losses. To separate no load losses into hysteresis and eddy current losses. This is simply my aims to conduct this test. Are you okay? Next, what are the specifications? What are the specifications? What is voltage? What is current? Generally, in this condition, in open circuited test, the voltage applied is rated value. And here, the current drawn by the machine, the current drawn by the transformer is I0. This I0 value is 2 to 6% of full load current. 2 to 6% of full load current. And here we have to take LPF wattmeter. LPF wattmeter. Here we are using LPF wattmeter. These are the specifications. Next, where we have to conduct this test, on LV side or HV side. Always the OC test should be conducted on should be conducted on LV side of transformer, LV side of my transformer. Open circuit test should be conducted on LV side of my transformer, because here we require a rated voltage. For example, my transformer is 200 by 400 volts. 200 by 400 volts transformer. If test conducted on LV side, we required only 200 volts supply source. If test conducted on HV side, we required 400 volts voltage source. Which is very easy. 200 volts is easy. So, like that. And if test conducted on this side, the voltmeter range up to 250 enough. But if test conducted on 400 volt side, the voltmeter range should be up to 500 volts. Which is easy? This one is easy. So simply for easy, for convenient, and for easy analysis, and for economic, and for easy maintenance, the test should be conducted on LV side. Another main thing also is there. If test conducted on HV side current is less, no load current is very less, negligibly less, the results may not be accurate. So to get the accurate results, the test should be conducted on LV side. This is simply where we have to do the test. The test should be conducted on LV side for convenience of meters, for convenience of meters, for convenience of supply source, and for easy calculations, and for good results. The test should be conducted on LV side. So this is LV side, and HV side is open circuited. LV side, HV side is open circuited. HV side is open circuited, and LV side is test conducted. LV side test conducted and HV side open circuited. This is simply about our open circuit test. First one is why we have to do, and what are the voltage and currents, and where we have to do. Now do the test. So let's do the test. We are applying rated voltage. When rated voltage applied to the machine, it draws a small current. By ammeter, we can calculate it I0 value. I0 value, we know that around how much? 2 to 6% of full load current. Then we have to note down this wattmeter reading. Generally, this wattmeter W0 gives us what it gives us. The W0 gives us no load losses of machine, no load losses of transformer, and also no load losses, and also very small primary copper losses. Also, because this I0 current flows through the primary winding. But we know that the copper losses depends on current. What is the current here? Just 2%, very small. That's why this primary copper losses are neglected. Now the wattmeter reading gives us the no load losses of the transformer only. So how much it is? This W0 is equals to V I0 cos pi naught, because this is a single phase transformer. If it is a three phase transformer, take 3 V I0 cos pi naught. This is the no load losses of my transformer I calculated. No load losses completed. Next one, no load parameters. From this, calculate no load power factor. No load power factor cos pi naught is equals to W naught upon Vi naught. For example, if you want to know load power factor angle, phi naught is equals to cos inverse of W naught upon Vi naught. This is no load power factor and no load power factor angle both. Here we know the vector diagram. Here voltage V, here IW, and here I mu, and this is my I naught. The angle between voltage and I naught is nothing but phi naught. This phi naught value, how much? This phi naught is equals to cos inverse of W naught by Vi naught. In generally, this phi naught value for our transformer, its value around 80 to 85 degrees, around 80 to 85 degrees, in the range of around 80 degrees. This value in the range of 80 degrees. Mostly 80, 85, 75 or 75 to 80 in the range. This is not accurate, approximate value, around 75 to 80 degrees. 75 to 80. See how much this is? Nearly 90, but not 90. Around 75 to 80 degrees. And the cos pi value, the no load power factor for transformer. No load power factor for transformer is around 0.2 to 0.25 lagging. 0.2 to 0.25 lagging, and this is around 75 to 80 degrees. We calculated the no load power factor and power factor angle. Next what we have to calculate? No load branch parameters. No load branch parameters nothing but R naught, X naught, IW, I mu of I naught, right? So let's calculate here. For example, let's take the equivalent circuit of no load. This is my no load equivalent circuit. R naught, X naught, I naught, R naught, X naught, I naught, and here the current is IW, here the current is I mu. This is phi naught. Now calculate IW. Calculate IW. I want IW. I know this is the hypotenuse and this is the I mu. If this is I mu, this is also I mu. So from this triangle, sin theta is equals to, or cos theta is equals to, cos phi naught is equals to, cos nothing but adjacent by hypotenuse, right? Cos nothing but adjacent. What is adjacent? Adjacent is the IW. Adjacent angle is the IW. And what is hypotenuse? Hypotenuse is the I naught. Now tell me, from this IW is equals to I naught cos pi naught. IW is equals to I naught cos pi naught. This is also important thing. Same as usually, take a sin theta from this. Take a sin theta. Sin phi naught is equals to opposite by hypotenuse. What is opposite angle? The opposite one is nothing but I mu. This is I mu, nothing but this is also I mu. So opposite side is I mu and hypotenuse is I naught. Then I mu is equals to I naught sine phi naught. I naught sine phi naught. This is IW. IW is equals to I naught cos phi naught and I mu is equals to I naught sine phi naught. These two are very important. Now we know this IW, we know this IW, and we know this I mu also. And I naught, we know I naught is equals to square root of IW square plus I mu square. It is a normal thing. IW square cos square, I naught square, I naught square sine square, I naught square cos square, I naught common, sine square cos square 1. Like that we can calculate. Very simple thing. Now, here the supply voltage is V. Of course, these are all are in parallel. Here also voltage V, here also voltage V. Now tell me, what is R naught from circuit? From the circuit, R naught is equals to R naught. We know the value rated voltage and we know the IW, I naught cos phi naught. So R naught is equals to V upon IW. V upon IW is equals to R naught. And what is X naught? X naught is equals to V upon I mu. X naught is equals to V upon I mu. R naught and X naught. V upon IW, V upon I mu. This is simply the no load parameters. I have R naught, I have X naught, I know the IW, I know the I mu, I know the phi naught. This is the no load parameters of my transformer. I calculated no load losses and I calculated no load parameters. These parameters are very important. Remember carefully. Next. Another small thing is remaining. What is that? To separate no load losses into hysteresis and eddy current losses. Hysteresis and eddy current losses. Okay. So before that, tell me, hysteresis losses and eddy current losses directly proportional to when V by F constant. When V by F constant, hysteresis loss is directly proportional to frequency and eddy current loss is directly proportional to frequency square. Yes or no? We calculated this one. From this, I am writing hysteresis losses is equals to some constant into frequency. Eddy current losses is equals to some constant into frequency square. Some constant into frequency square. Just remember this. Now I am going to separate this no load losses into hysteresis and eddy current losses. For that we have to take a graph. This graph between frequency and W naught by frequency. Frequency and W naught by frequency. We have to take this graph. And for each and every frequency, at 10 edges, 20 edges, 30 edges, 40 edges, 50 edges, 60 edges, like that, for each and every frequency, calculate the W naught value and divide with frequency and take a graph. For example, if you take a graph, the graph will comes like this. The graph will comes like this. If you draw the line it goes like this. For example, this is some constant A and this is slope with some slope b. It's a slope b. For example, I assumed this is some constant a and it is the line with slope b. What is the formula for this one? What is the formula for this one? When the line is posing like this at constant, this is x-axis and this is y-axis and this is a slope m. Then what is the formula? Y is equals to mx plus c. Yes or no? Y is equals to mx plus c. What is y here? Here y is the W naught by frequency. Y is equals to mx. What is m here? Here slope is the b and x is the frequency. Y is equal to mx plus c. What is constant here? Here the constant is a. Then W naught is equals to bf square plus af. W naught is equals to bf square plus af. From this equation, W naught is nothing but no load losses is equals to bf square nothing but eddy current losses and af nothing but hysteresis losses. This is the separation of losses, separation of iron losses into eddy current and hysteresis losses. This is also very important. They will ask you question in your GATE exam. This is separation of losses. Separation of losses. Right? This is simply our transformer open circuit test. Now tell me, once rapid reverse. Tell me, sir. Finally, what we done? The separation of losses. Before that, what we done? The calculation of no load parameters. Before that, what we done? The calculation of no load losses. Before that, what is the specifications and what is the aim? So tell me, what is the aim? To find out the no load losses and to find out the no load parameters and to find out to separate the no load losses into hysteresis and eddy current losses. What are the voltage? Voltage is the rated voltage. What is the current? 2 to 6% of full load current, which is called as no load current. What is the wattmeter we are using? LPF wattmeter, because here the power factor is less than 0.5. If the power factor is less than 0.5, then we have to use LPF wattmeter. Right, where we have to done the OC test, the open circuit test should be conducted on LV side and HV side should be open circuited for easy calculations, for easy maintenance, for convenience of meters, for good results. The test should be conducted on LV side, conducting nothing but connecting the supply. And next one, what wattmeter reading gives us? The wattmeter reading gives us no load losses as well as primary copper losses, but those are very small, that's why negligible. We have only no load losses. No load losses formula V I naught cos pi naught. From that power factor and power factor angle calculated, its approximated values. Then after, from this cos pi and sin pi, I calculated IW and I mu. I naught is nothing but the sum of IW and I mu. Then after, from this I calculated R naught and X naught. And then after, I done a test with V by F constant. V by F constant, like a 10 volts, 10 edges. Next, 20 volts, 20 edges. 30 volts, 30 edges. 40 volts, 40 edges. Like that, up to some points. Then I draw a curve. From this curve, the equation of the curve y is equal to mx plus c. From that, the no load losses is exactly equals to eddy current losses and hysteresis losses. We can conclude them. Yes or no? Are you okay? Right? This is the open circuit test of the transformer. Let's see some different questions, how they will ask you in competitive exams. on open circuit test. Now they will ask you question OC test conducted on a transformer OC test conducted on a transformer with rated voltage, reduced frequency, with rated voltage, reduced frequency. Then what happens? With rated voltage, reduced frequency. Then what happens? So see here. First, see here, B maximum is directly proportional to V by F, I said you. Here, rated voltage but reduced frequency. When the frequency reduces, then the flux density increases. When frequency reduces, then flux density increases. When flux density increases, automatically flux also increases. When flux increases, nothing but automatically I mu increases. Yes or no? Automatically I mu increases. Let's see. This is phi. Actually here IW, actually here I mu, and sum of these two is I naught. Here IW and I mu, actually like this. But when the test conducted with the rated voltage and reduced frequency, then B maximum increases and flux increases. When flux increases, automatically I mu increases. Like this. I mu increases. Actually, this is our phi naught, no load power factor angle. But when our flux increases, then I mu increases. Automatically, I naught also increases. What happens, sir? When I mu increases, I naught also increases. When I naught increases, see here, the power factor angle also increases. When power factor angle increases, power factor decreases. This is important. A test conducted with rated voltage, reduced frequency. When frequency reduces, flux density increases, flux increases, I mu increases. When I mu increases, I naught increases. Power factor angle increases. Simply, power factor decreases. Rated voltage, reduced frequency results in reduction in power factor. Sir, what about IW? IW constant is correct answer. Or slightly increases is also correct answer. Constant or slightly increases. Effective increase, that's it. This is simply what happened to power factor, what happened to current. At this condition, what happened to current? The no load current increases and the power factor decreases. No load current increases and the power factor decreases. When the no load current increases, W naught is equals to V I naught cos pi naught. When the no load current increases, automatically no load losses also increases. So another conclusion, no load losses also increases with rated voltage reduced frequency. No load current increases, power factor decreases, power losses increases. This is the first case. What is the first case? Rated voltage, reduced frequency. What is the next case? Rated voltage, increased frequency. What is the next case? Reduced voltage, rated frequency. What is the next case? Increased voltage, rated frequency. Like this, we have a 4 cases. I done just one case. You have to do these 3 cases. They may ask you any one of this, but very important for any competitive exams. So what happened to current, power factor, power? This is also, we can give answer directly. How directly? We know that hysteresis losses and eddy current losses formula. Here I said you rated voltage but reduced frequency. Rated voltage but reduced frequency. For example, my rated voltage 200 volts, my frequency 50 Hz actually. But now voltage is same but frequency reduced. This is V by F constant or not? First V by F is the 4. First V by F is equals to 4. Next, after changes, rated voltage, reduced frequency. Now V by F is 8. Is V by F constant? No sir, V by F not constant because voltage is constant but frequency reduced. If both are constant, okay, no problem. If both are reduced, no problem. If both are increased, no problem. But one is constant, one is reduced. This is not constant. V by F not constant. V by F not constant. If V by F not constant, what is hysteresis losses? If V by F not constant, hysteresis losses formula. Hysteresis losses formula is this one. If V by F not constant. And what about eddy current losses? If V by F not constant, eddy current losses formula is this one. Now tell me, what happened to hysteresis and eddy current losses? When voltage is rated, nothing but voltage is common. There is no changes in voltage. What happened to frequency? Frequency reduces. When frequency reduces, what happened to hysteresis losses? If frequency reduces, hysteresis losses increases. Hysteresis losses increases. What happened to eddy current losses? Eddy current losses are constant. Eddy current losses are constant because these are only depends on voltage. Only depends on voltage. Finally, hysteresis losses increases and eddy current losses no change. Eddy current losses no change. Then what happened? Finally, the no load losses nothing but hysteresis and eddy current losses. Hysteresis losses increases, that's why the no load losses also increases. That's why the no load losses also increases. We can say directly, but in this method we can say only about no load losses. We don't know about current and power factor. By this method we can calculate current, power factor and no load losses. If they ask you only what happened to no load losses, or what happened to hysteresis losses, or what happened to eddy current losses, then go for this. Okay. Let's see another same question for this. Same question for this. Reduced voltage, rated frequency. Reduced voltage, rated frequency. What happened to hysteresis, eddy current and no load losses? Tell me. Reduced voltage, rated frequency, V by F not constant. If V by F not constant, hysteresis losses directly proportional to V power 1.6 upon F power 0.6. Frequency is the rated value, but voltage decreases. when voltage decreases, hysteresis losses also decreases. Is completed. What happened to eddy current losses? Eddy current losses directly proportional to V square. When voltage decreases, automatically eddy current losses also decreases. Automatically eddy current losses also decreases. Now tell me what happened to no load losses? No load losses nothing but hysteresis and eddy current losses. Hysteresis losses reduces, eddy current losses reduces, so no load losses also reduces. No load loss also reduces. Like this we can conclude directly. But if they ask you what happened to no load current, what happened to power factor, go through this one. Go through this one. This is very important. A small question. If air gap increases in the transformer, then what happened to power factor? Especially they will ask you power factor. Not only in transformer, this question is applicable for all machines. If air gap increases, then what happens? Let's see. Actually, this is our vector diagram. Here IW and here I mu, and sum of these two is taken as I naught, and this is the no load power factor angle phi naught. But they said that air gap increases. If air gap, nothing but L, if air gap increases, then what happened to reluctance? Reluctance S is equals to L by mu A. If air gap increases, then automatically reluctance increases. If reluctance increases, what happened to flux? Flux phi is equals to MMF by S. If reluctance increases, then flux decreases. What happens, sir? If air gap increases, flux decreases. When the flux decreases, to compensate that flux, actually 10 Webers is there. Due to air gap increased, the flux reduced to 8 Webers. This is not enough. I want 10 Webers of flux. Transformer said that to the supply. No, I'm sorry, just I have 8 Webers, but I want 10 Webers of flux. Then what happened? The transformer, to compensate this 2 Webers of flux, it draws the more current from the supply. What happens, sir? It draws the more current from the supply, which is flux component IW or I mu. I mu is the flux component, right? Magnetizing component, right? So to compensate this 8 Webers to 10 Webers, nothing but the 2 Webers, the transformer draws the extra magnetizing current. This is our magnetizing current, new magnetizing current. So when air gap increases, reluctance increases. When reluctance increases, flux reduces. Then the electrical machine draws more magnetizing current. First important point. When air gap increases, the machine draws more magnetizing current. When magnetizing current increases, then automatically no load current also increases. When air gap increases, magnetizing current increases and no load current increases. When no load current increases, then ultimately no load power factor angle increases. No load power factor angle increases. When no load power factor angle increases, no load power factor decreases. Very, very, very important. When air gap increases, then the power factor decreases in any machines. When air gap increases, power factor decreases. Before that, I mu increases, I naught increases, phi naught increases, then power factor reduces. This is very important question for competitive exams, right? Thank you.